CHAG Advanced Control, the convergence of intelligence, automation, and operational excellence. Advanced control represents the synthesis of process engineering, model based automation, and digital intelligence. It is not a single algorithm or technology, but a comprehensive approach to controlling industrial processes with higher precision, responsiveness, and economic awareness than traditional methods allow. In modern industrial operations, advanced control serves as the central nervous system, linking local regulation, supervisory optimization, and business objectives through coordinated layers of control logic. It is characterized by its ability to predict, adapt, learn, and optimize. Defining advanced control in today's context. Historically, advanced control referred to any strategy more sophisticated than classical proportional integral derivative (PID) control. Today, it encompasses a wide array of interconnected systems and methods, including model predictive control (MPC), adaptive and self-tuning control systems, multivariable control (MVC), nonlinear and globally linearizing control, artificial intelligence (AI) driven supervisory control, real-time optimization (RTO), statistical process control (SPC), integration, fault detection and diagnosis (FDD), inferential sensing (soft sensors). These components operate within a layered architecture, enabling real-time decisions that align with broader performance goals: yield, efficiency, safety, quality, and sustainability. The hierarchy of advanced control. Advanced control systems are typically organized into three integrated layers: local control, regulatory layer. Basic PID controllers ensure fast, stable control of individual variables, e.g., pressure, flow, temperature. Advanced Regulatory Control (APC) layer includes MPC, feed-forward, cascade, and constraint-based logic. These controllers manage interacting loops, dead time, and nonlinearities. Supervisory and Optimization layer performs economic optimization, constraint coordination, and set point scheduling. It bridges real-time control with planning systems like MES, Manufacturing Execution Systems, and ERP, Enterprise Resource Planning. Each layer is designed to be modular but tightly connected. Information flows vertically, allowing higher layers to influence strategy and lower layers to execute with precision. Core capabilities of advanced control: prediction and look ahead. Using dynamic models, controllers forecast future process behavior and optimize inputs accordingly. Constraint handling. Controllers respect operational limits, e.g., temperature, flow, emissions, enabling operation closer to process boundaries without risk. Multivariable coordination, simultaneous control of multiple inputs and outputs while accounting for cross-loop interactions. Adaptation, real-time model updates or gain adjustments in response to changing conditions, e.g., catalyst aging, feedstock variation. Optimization, aligning control decisions with economic and environmental performance through cost functions and profit constraints. Fault detection and resilience. Early warning systems, redundancy, and fallback strategies preserve uptime and product quality. Enabling technologies. Advanced control systems draw upon a wide toolkit of enabling technologies. Process models, mechanistic, data-driven, hybrid, soft sensors and inferential estimators, digital twins for simulation and testing, AI and machine learning for pattern recognition, estimation, and decision support, data integration platforms, e.g., OPC UA, cloud connectors, cybersecurity frameworks to protect control integrity. The result is a control environment that is not only responsive but intelligent and context-aware. Real-world impact. Advanced control systems deliver measurable benefits across industries: 2 to 6% reduction in operating costs, 10 to 30% reduction in energy use or emissions, improved yield and throughput, better consistency and quality assurance, fewer alarms, trips, and operator interventions, increased flexibility for multi-product or dynamic production schedules. Industries benefiting include oil and gas, chemicals, pharmaceuticals, food and beverage, power generation, water treatment. Conclusion: advanced control is the digital command layer of the modern industrial plant. It unifies process knowledge, predictive modeling, and intelligent automation into a system capable of continuous learning, adaptation, and optimization. Far beyond traditional loop tuning, it is a strategic capability, transforming data into action and control into competitive advantage. As industries move towards smart manufacturing, sustainability, and autonomy, advanced control will remain the foundation of resilient, future ready operations. Current research and future trends shaping the next generation of intelligent process control. As process industries evolve toward higher levels of automation, sustainability, and digital integration, advanced control is entering a new era, one shaped by artificial intelligence, AI, data centric design, and systems that learn, adapt, and collaborate. The ongoing research and emerging trends reflect a collective drive to build smarter, faster, and more resilient control systems capable of operating under uncertainty, dynamic market pressures, and increasingly complex plant configurations. The future of control lies not in replacing foundational principles, but in augmenting them with computational intelligence, human machine synergy, and new modeling paradigms that blend data and domain knowledge. Key areas of active research: neural networks and deep learning for control. Use of artificial neural networks, ANNs, and deep learning architectures to build highly accurate models of nonlinear processes. Applications in predictive control, soft sensors, and fault classification. Techniques for real-time learning and adaptation in dynamic environments. Hybrid modeling approaches that combine first principles physics with neural approximators, gray box models. Nonlinear and multivariable predictive control. Development of scalable nonlinear model predictive control (NMPC) frameworks. Integration of multivariable nonlinear models with economic objectives. Research on real-time optimization (RTO) and VEST economic MPC to directly link control actions with profit and sustainability targets. Robust and resilient control architectures. Advanced, robust control strategies that tolerate uncertainty and variability without compromising performance. Emphasis on fault-tolerant control systems that adapt to hardware, software failures, and process disturbances. Use of probabilistic models, interval observers, and set-based estimation to characterize uncertainty. Integration of AI and expert systems. Real-time knowledge-based supervision using expert systems, fuzzy logic, and symbolic reasoning. AI-powered operator advisory systems and decision support tools that assist with set point selection, alarm rationalization, and anomaly resolution. Growing adoption of real-time knowledge-based systems, RTKBS, to supervise adaptive controllers and multivariable logic. Digital twins and hybrid simulation platforms. Use of digital twins for controller testing, operator training, and scenario analysis. Platforms that synchronize simulation and real-time data for what-if testing and performance prediction. Integration with cloud-based analytics, enabling remote access to optimization and diagnostics layers. Emerging trends and future directions. Gray box and hybrid modeling. Blending mechanistic models with machine learning for greater interpretability and flexibility. Use of hybrid digital twins that combine physics, AI, and real-time feedback for real-world predictive control. Cloud and edge-based control. Deployment of control and analytics logic at the edge, close to sensors and actuators, for faster response times and lower latency. Cloud-based model deployment, versioning, and optimization support. Scalable infrastructure for monitoring thousands of assets across distributed plants. Self-configuring and self-healing systems. AI-enabled controllers that auto-tune, self-optimize, and reconfigure in response to system degradation or changing objectives. Integration with condition-based maintenance and asset health management. Enhanced human-machine interfaces, HMI, and operator empowerment. Development of intuitive HMIs using augmented reality, AR, natural language interfaces, and predictive diagnostics dashboards. Human-in-the-loop systems that balance automation with oversight, enhancing decision-making without removing human agency. Formal verification and control integrity. Research into the verification of AI and neural network-based control systems for industrial safety and compliance. Development of frameworks to validate control logic across a range of operating conditions and disturbances. Bridging technology and talent. Despite rapid technological progress, a key barrier remains: the adoption and integration of advanced control techniques within existing operations. Current research is addressing Low-code, no-code configuration platforms for engineers without deep control theory backgrounds, training tools and digital learning systems to upskill the workforce, standardization and open integration frameworks to ease deployment across vendors and platforms. Conclusion: the future of advanced control is not just about smarter algorithms, it's about building intelligent, resilient, and human aware control ecosystems. The convergence of control theory, machine learning, and digital infrastructure is redefining what is possible in process automation. From autonomous optimization to self adaptive digital twins, the next generation of control systems will not only respond to the process, they will understand it, anticipate it, and improve it continuously. These technologies will underpin the industrial transitions ahead towards sustainability, agility, and operational excellence. The transformative role of historical process data and AI-driven model usage in modern control. Historical process data, once used primarily for reports and audits, has become one of the most strategic assets in industrial control. When coupled with advanced models and artificial intelligence AI agents, this data is transformed from a passive archive into a dynamic foundation for proactive, predictive, and adaptive process control. By leveraging large volumes of time series data collected from sensors, valves, controllers, and lab systems, modern control environments can now learn system behavior, detect unseen correlations, and act ahead of deviations, not just after they occur. This shift from reactive to intelligent control marks a turning point in automation maturity. How historical data enhances control. 1. Data-driven model generation and refinement. Historical data enables the development of black box models, e.g., RX, NARX neural networks, that accurately capture system dynamics without physical equations, hybrid models that blend empirical data with mechanistic knowledge, anomaly detection models trained on baseline performance patterns. These models improve over time, evolving as more process data becomes available, turning every batch, cycle, or shift into training input. 2. Identification of non-obvious correlations. AI agents can discover complex, nonlinear, and multivariable correlations that are not easily seen by operators or engineers. Input-output relationships buried in noise or long-time delays, interactions between seemingly unrelated variables, e.g., ambient temperature and final product quality, hidden patterns tied to equipment wear, fouling, or gradual drift. By learning these dependencies, control systems can better predict process changes and correct them earlier. Proactive control through AI-based correlation. AI agents built using machine learning, ML, deep learning, or symbolic reasoning take historical and real-time data and turn it into actionable control intelligence. Their functions include predictive regulation. Predict disturbances, quality shifts, or constraint violations before they occur. Adjust set points or control moves in anticipation of upsets. Reduce lag in control action, especially in slow or batch processes. Soft sensor deployment. Infer key quality or safety metrics, e.g., purity, reaction conversion, from indirect variables. Replace or supplement infrequent lab measurements or missing field instrumentation. Provide continuous feedback for model predictive control, MPC, or feedback tuning. Chat autonomous loop tuning and adaptation. Detect controller performance degradation, offset oscillation, recommend or automatically apply new PID MPC parameters. Retune models when plant conditions shift, e.g., new feedstock, catalyst deactivation. Her root cause diagnosis and fault prevention. Correlate deviations to specific upstream conditions or control changes. Alert operators with cause and effect trails with not just symptoms. Modify control sequences to avoid repeat incidents. Use case example, AI agent in a distillation column. Historical data reveals that reboiler fouling causes subtle shifts in temperature profile days before quality drops. An AI agent trained on that pattern identifies the trend early and adjusts reflux and overhead pressure to compensate. It alerts maintenance for proactive cleaning and retunes the MPC model to account for thermal resistance change. Outcome: no quality loss, no alarm floods, and no unscheduled shutdown. Integration with control architecture. These capabilities are embedded within a modern layered control system. Field layer. Sensors feed data continuously. Control layer, MPC and PID loops act in milliseconds to minutes. Supervisory layer. AI agents evaluate long-term patterns and evolving trends. Enterprise layer. Historical models are compared across shifts, units, and plants for strategic insight. AI agents do not replace traditional control, they enhance it by operating in the time scales and complexity layers where human intervention or static models fall short. Conclusion. The integration of historical process data, advanced modeling, and AI driven analysis is redefining how processes are controlled and monitored. Instead of reacting to symptoms, modern systems learn from the past, sense the present, and shape the future, controlling not just variables, but outcomes. With these tools, plants move from deterministic automation to adaptive intelligence, unlocking new levels of efficiency, stability, and agility. As AI becomes increasingly embedded in the industrial fabric, it enables proactive control ecosystems where decisions are faster, smarter, and deeply informed by the system's own history. Enhancing feedstock utilization and product quality with artificial intelligence models, driving efficiency and precision through intelligent automation. In the evolving landscape of process industries, where raw materials are increasingly variable, margins are tighter, and quality requirements are uncompromising, artificial intelligence AI models offer transformative potential. By learning from vast historical data sets, adapting in real time, and optimizing multivariable decisions, AI enables plants to both maximize feedstock utilization and sharpen product quality simultaneously. Unlike traditional control systems that follow static logic, AI-driven systems dynamically understand, predict, and optimize the process across shifting feed conditions and quality targets. This creates a smarter production loop that responds to real-time variations with precision, turning uncertainty into opportunity. Optimizing feedstock utilization with AI. Raw materials often represent the largest cost in process operations. Their composition, consistency, and quality may vary significantly due to supplier differences, seasonal or geographical sourcing, storage, transportation, and weather impacts, recycling and circular economy practices. AI models help overcome these challenges by transforming raw material variability into a controllable and optimizable parameter. Key AI capabilities for feedstock optimization. Feed characterization via soft sensors. AI models can infer real-time feedstock composition, sulfur content, moisture density, using easily available process signals. This eliminates dependence on lab delays or unavailable instrumentation. Feed process matching. Intelligent agents recommend how best to run the process based on current feed properties. For instance, adjust reactor temperature or residence time for a lower reactivity feed. Modify distillation cut points to extract more value from blended crude. Tune catalyst dosing or additive use dynamically. Waste reduction and yield maximization. AI detects when feed quality could lead to increased waste or off-spec material and automatically adjusts control settings to minimize losses. It enables optimal feed-to-product conversion, improving yield without operator intervention. Real-time economic optimization. Machine learning models continuously assess the trade-offs between feed variability, energy consumption, and product profitability. AI helps prioritize feedstock usage that delivers the highest value per unit cost, not just the easiest to process. Sharpening product quality with AI intelligence. Meeting product quality specifications is central to operational success, regulatory compliance, and customer satisfaction. AI models significantly enhance quality control and prediction, especially when traditional measurement systems fall short. Key AI contributions to quality enhancement. Predictive quality modeling. AI systems use past data to anticipate quality deviations, often hours before they show up in final product or lab reports. For example, predicting polymer melt index, forecasting distillate sulfur content, anticipating pH or viscosity in specialty chemicals. Closed-loop quality adjustment. Based on AI quality predictions, control systems can adjust raw material blending, fine-tune process conditions, e.g. flow, heat, pressure, recommend set point changes that improve final product consistency, reduction in rework and off-spec batches. AI-powered classification and regression models flag conditions likely to result in non-conforming products, allowing corrective actions before material is committed. Adaptive control for tight tolerances. In industries like pharmaceuticals, semiconductors, or food, where specifications are razor thin, AI ensures real time conformance through drift compensation, equipment condition adjustment, data driven feedback to optimize control loop parameters. Synergizing feedstock and quality control. AI doesn't treat feedstock and quality as separate challenges, it connects them. It learns how variations in feed impact quality outcomes, enabling intelligent trade offs and dynamic adaptation. Example: in a refining process, if high density crude is fed into the unit, AI may suggest a slower feed rate, higher energy input in distillation, earlier cut point transitions. Result: despite variable feed, the AI maintains diesel yield and sulfur content within target specs, optimizing quality while preserving throughput. Implementation across the control stack. AI models enhance operations at every layer: field level, predictive soft sensors for unmeasured feed parameters, control level, model predictive and adaptive set point tuning based on AI insights, supervisory level, AI recommended production profiles to balance cost, quality, and efficiency, enterprise level, continuous learning from past campaigns used to refine future production strategies. Integration with digital twins, cloud analytics, and real time optimization frameworks ensures that AI outputs are not just theoretical, they drive actionable improvements. Artificial intelligence models are redefining how industries manage feedstock variability and product quality. By learning from history, analyzing live data, and predicting future behavior, AI systems extract more value from every raw material input, reduce dependency on lab results or operator intuition, deliver higher quality products with fewer interventions, minimize energy and raw material waste, create a more agile, adaptive, and profitable operation. Ultimately, AI turns variability into a competitive advantage, enhancing both input efficiency and output excellence in real time.